Greetings everybody. So let's kind of continue our discussion with our binormal vectors now and kind of see where this one's going. And so we had our orthogonal complement of the derivative of our unit normal. That was just going to be our dn ds minus our projection, and our projection was our negative of the curvature times the unit tangent. And so this whole vector dn ds plus kappa times t was going to be our orthogonal complement to t of our vector dn ds. And so if we kind of continue with this, if we look at the projection of that vector onto our unit normal vector, so we're taking the dot product here, we're looking at the magnitude of this projection, then our dot product distributes across those sums. So this is going to be the dot product with dn ds and the dot product of kappa t and n. Well, again, because our unit normal is a unit vector, always a unit vector, when we take the derivative with respect to the arc length of that one, then remember that these two guys are going to be orthogonal as well, just like it was with the unit tangent vector, so it's going to be with the unit normal vector. So these guys are going to be orthogonal, so we get a 0 out of that one. But then also the unit tangent and the unit normal are orthogonal, so we get another 0 out of this one. So this vector, dn ds plus kappa times t, it is not in the direction of the unit normal at all. Okay, so this thing is not in the direction of the unit tangent because it was the orthogonal complement to the unit tangent. It's not in the direction of the unit normal, as we just saw here. And so what's going on there? What does that leave us with? That since we're in 3 dimensions, the only option that we really have left is the vector that's going to be perpendicular to both t and n. Well, that leaves us with our binormal vector. And so if we look at the projection of this complement, orthogonal complement onto the binormal vector, we do the same thing. We take the dot product. Remember, again, from a previous video, this thing is also going to be a unit vector. So if we take the inner product, the dot product of that thing, that's going to be the magnitude of our projection as well. And so what this thing is going to be, we distribute our binormal vector across both of those. And again, remember that the binormal, because it's a cross product, was perpendicular to the unit tangent, so that one's going to go to 0. And what this leaves us with is just this projection of the binormal vector onto the derivative of the unit normal. And that derivative onto the unit normal, we're going to give that one a name of a new function and call this the torsion of the curve. Okay, so now kind of what we've got the curvature, which kind of explains how this thing is curving if it were a plane vector. So if this vector was only contained in the plane, here's kind of the forces that are keeping it curving in that plane. Well, when we go to 3 dimensions, there's nothing to hold us in a plane anymore, and so we could talk about how it's kind of being forced out of that plane. So we're kind of torquing, we're torsioning this thing out of its regular plane curve to force us into 3 dimensions, and that's really what the torsion is giving us in this case. And so kind of putting all of this together, what we had, our orthogonal complement, was the torsion times the binormal vector. And that was our projection onto that direction. And so if we kind of put these things together, we get a derivative of our unit normal is just the negative of the curvature times the tangent, unit tangent, plus the torsion times the binormal vector. And so again, kind of that torsion is giving you the measure of how much this curve is kind of rotating out of the plane in which it's contained. So we've got a plane vector. If we imagine we kind of take this thing, we take either side, so the point on the curve, we take either side and we kind of grab it on either side and we pry it out of the plane that it's contained in. The amount that we're kind of prying it out of that plane is really what torsion is getting for us. And so finally, kind of coming back to this binormal vector again as the cross product. So if we look at the derivative of the binormal vector with respect to arc length, then what happens? Well, remember that we have this kind of product rule property even with our cross products. So we get dt ds cross n plus t cross dn ds. Well, dt ds is parallel to the unit normal vector, and so if I cross a vector with itself, that's automatically 0. We figured out what dn ds was. That was the negative of kappa of t plus the torsion times the binormal vector. Well, if we cross it here, again, the cross product's going to distribute across those things. So a vector cross itself is 0, so that one cancels out and it goes away. And so now I've got the unit tangent crossed with the binormal vector. Well, the binormal vector itself was a cross product, and so now I'm applying a vector identity that we have. If we take the cross product of a vector that's already a cross product, it ends up being this expression where we're doing the dot product of the first vector with the third vector, and that's scaling the second vector, minus the dot product of the first vector and second vector, and that's scaling this third vector. And so if we do that, apply that formula in this case, well, we get t cross n, but or t dot n. Remember, t dot n, these guys are orthogonal, so that's 0. T dot t is a unit vector, so that's 1. And so we end up with just negative of our torsion times the unit normal vector. So if we kind of take all of these things and put them together, what we're seeing is that we've got these three vectors, our t and our n and our b, so our tangent vector, normal vector, and binormal vector. These kind of constitute the t and b frame for every point that's along our curve. So we're really introducing a three-dimensional coordinate system attached to every single point on a curve. And by looking at how those things change, so remember our derivatives, how these things are changing with respect to the arc length of our curve, we kind of get this, how we can describe that our curve is evolving as we move along through time. That what happens with these things, well, and we have this thing expressed totally in terms of the vectors of our three-dimensional coordinate system itself, our t, our n, and our b. Now, these kind of frame evolution equations that we've got go together as what are called the frenet-serret equations. And if you're doing a lot of kind of modeling of curves, you can kind of put things into that t and b frame, and kind of another theorem that goes along when you're looking at these things later is that these guys actually give a total description of how this curve is really going to move in three-dimensional space. That if we know the curvature and if we know the torsion, then that's going to uniquely get us, quote, almost uniquely, get us a vector curve that will move in that way. So we've kind of got all of the possible information that we could have contained in those things, in those three kind of coordinate vectors in this frame, in this T and B frame. So let's take a look at maybe Geogebra to get an idea of how these things are really looking. And so here I've already got a curve kind of made up that this thing is really just going to be a spiral that's heading down the x-axis. And so what I've got here, kind of what we drew before, we've got our unit tangent vector being this blue one that's going to be in the direction of the curve. We've got our unit normal vector that's going to be kind of perpendicular to that. And if we kind of imagine that we're in the plane of this curve, so if we're right there kind of parallel with our normal and our tangent, then we've got this green vector that's our binormal vector. So if this thing were a plane curve, so living just in one single plane, all we would have is our tangent vector and our normal vector. And our binormal vector would just be constant, okay? But it's not. This thing will change. We've got a three-dimensional coordinate system attached to this curve, and if we kind of move things around, you can see really what happens to that coordinate system, that it's going to rotate and move as we move around this curve. And so as we kind of move from there, let's kind of switch this so we can see a little bit more of the curve there for what's happening. Now let's move around our curve. We see that our coordinate system is kind of changing as we're moving along the curve, but we can describe everything about that curve in terms of that T and B frame. So that's kind of why our tangent, normal, binormal vectors are important. We're going to talk about moving of curves in three-dimensional space and kind of how they're related. We've got our curvature, we've got our torsion, and so I kind of hope this puts a lot of these pieces together for you to let you see maybe what's going on, and I will see you guys next time.